Low-pass filter.
A low-pass filter is a filter that passes low-frequency signals and attenuates signals with frequencies higher than the cutoff frequency. The actual amount of attenuation for each frequency varies depending on specific filter design. It is sometimes called a high-cut filter, or treble cut filter in audio applications. A low-pass filter is the opposite of a high-pass filter. A band-pass filter is a combination of a low-pass and a high-pass. Low-pass filters exist in many different forms, including electronic circuits, such as a His filter used in audio, anti-aliasing filters for conditioning signals prior to analog to digital conversion, digital filters for smoothing sets of data, acoustic barriers, blurring of images, and so on. The moving average operation used in fields such as finance is a particular kind of low-pass filter, and can be analyzed with the same signal processing techniques as are used for other low-pass filters. Low-pass filters provide a smoother form of a signal, removing the short-term fluctuations, and leaving the longer-term trend. An optical filter can correctly be called a low-pass filter, but conventionally is called a long-pass filter. Low frequency is long wavelength, to avoid confusion.
Examples of low-pass filters. Acoustic.
A stiff physical barrier tends to reflect higher sound frequencies, and so acts as a low-pass filter for transmitting sound. When music is playing in another room, the low notes are easily heard, while the high notes are attenuated.
Electronic.
In an electronic low-pass LC filter for voltage signals, high frequencies in the input signal are attenuated, but the filter has little attenuation below the cutoff frequency determined by its LC time constant. For current signals, a similar circuit, using a resistor and capacitor in parallel, works in a similar manner. See current divider discussed in more detail below. Electronic low-pass filters are used on inputs to subwoofers and other types of loudspeakers, to block high pitches that they can't efficiently reproduce. Radio transmitters use low-pass filters to block harmonic emissions that might interfere with other communications. The tone knob on many electric guitars is a low-pass filter used to reduce the amount of treble in the sound. An integrator is another time-constant low-pass filter. Telephone lines fitted with DSL splitters use low-pass and high-pass filters to separate DSL and POT signals sharing the same pair of wires. Low-pass filters also play a significant role in the sculpting of sound created by analog and virtual analog synthesizers. See subtractive synthesis.
Ideal and real filters.
An ideal low-pass filter completely eliminates all frequencies above the cutoff frequency while passing those below unchanged. Its frequency response is a rectangular function and is a brick wall filter. The transition region present in practical filters does not exist in an ideal filter. An ideal low-pass filter can be realized mathematically, theoretically, by multiplying a signal by the rectangular function in the frequency domain or, equivalently, convolution with its impulse response, a sinc function, in the time domain. However, the ideal filter is impossible to realize without also having signals of infinite extent in time, and so generally needs to be approximated for real ongoing signals, because the sinc function's support region extends to all past and future times. The filter would therefore need to have infinite delay, or knowledge of the infinite future and past, in order to perform the convolution. It is effectively realizable for pre-recorded digital signals by assuming extensions of zero into the past and future, or more typically by making the signal repetitive and using Fourier analysis. Real filters for real-time applications approximate the ideal filter by truncating and windowing the infinite impulse response to make a finite impulse response. Applying that filter requires delaying the signal for a moderate period of time, allowing the computation to see a little bit into the future. This delay is manifested as phase shift. Greater accuracy in approximation requires a longer delay. An ideal low-pass filter results in ringing artifacts via the Gibbs phenomenon. These can be reduced or worsened by choice of windowing function, and the design and choice of real filters involves understanding and minimizing these artifacts. For example, simple truncation causes severe ringing artifacts in signal reconstruction, and to reduce these artifacts one uses window functions, which drop off more smoothly at the edges. The Whittaker-Shannon interpolation formula describes how to use a perfect low-pass filter to reconstruct a continuous signal from a sample digital signal. Real digital to analog converters use real filter approximations.
Continuous time low-pass filters.
There are many different types of filter circuits, with different responses to changing frequency. The frequency response of a filter is generally represented using a bowed plot, and the filter is characterized by its cutoff frequency and rate of frequency roll-off. In all cases, at the cutoff frequency, the filter attenuates the input power by half or 3 decibels. So the order of the filter determines the amount of additional attenuation for frequencies higher than the cutoff frequency. A first-order filter, for example, reduces the signal amplitude by half, so power reduces by a factor of 4, or 6 decibels, every time the frequency doubles, goes up 1 octave. More precisely, the power roll-off approaches 20 decibels per decade in the limit of high frequency. The magnitude bowed plot for a first-order filter looks like a horizontal line below the cutoff frequency, and a diagonal line above the cutoff frequency. There is also a knee curve at the boundary between the two, which smoothly transitions between the two straight-line regions. If the transfer function of a first-order low-pass filter has a zero as well as a pole, the bowed plot flattens out again, at some maximum attenuation of high frequencies. Such an effect is caused for example by a little bit of the input leaking around the one-pole filter. This one-pole 1-0 filter is still a first-order low-pass. See pole zero plot and RC circuit. A second-order filter attenuates higher frequencies more steeply. The bowed plot for this type of filter resembles that of a first-order filter, except that it falls off more quickly. For example, a second-order Butterworth filter reduces the signal amplitude to 1/4 its original level every time the frequency doubles, so power decreases by 12 decibels per octave, or 40 decibels per decade. Other all-pole second-order filters may roll off at different rates initially depending on their Q factor, but approach the same final rate of 12 decibels per octave. As with the first-order filters, zeros in the transfer function can change the high-frequency asymptote. CRLC circuit, third and higher-order filters are defined similarly. In general, the final rate of power roll-off for an order all-pole filter is decibel per octave, that is, decibel per decade. On any Butterworth filter, if one extends the horizontal line to the right and the diagonal line to the upper left, the asymptotes of the function, they intersect at exactly the cutoff frequency. The frequency response at the cutoff frequency in a first-order filter is 3 decibels below the horizontal line. The various types of filters, Butterworth filter, Chebyshev filter, Bessel filter, etc. all have different-looking knee curves. Many second-order filters have peaking, or resonance that puts their frequency response at the cutoff frequency above the horizontal line. Furthermore, the actual frequency where this peaking occurs can be predicted without calculus, as shown by Cartwright et al. For third-order filters, the peaking and its frequency of occurrence can too be predicted without calculus as recently shown by Cartwright et al. See electronic filter for other types. The meanings of low and high, that is, the cutoff frequency, depend on the characteristics of the filter. The term low-pass filter merely refers to the shape of the filter's response. A high-pass filter could be built that cuts off at a lower frequency than any low-pass filter, it is their responses that set them apart. Electronic circuits can be devised for any desired frequency range, right up through microwave frequencies, above 1 GHz, and higher.
Laplace notation.
Continuous time filters can also be described in terms of the Laplace transform of their impulse response, in a way that lets all characteristics of the filter be easily analyzed by considering the pattern of poles and zeros of the Laplace transform in the complex plane. In discrete time, One can similarly consider the Z transform of the impulse response. For example, a first-order low-pass filter can be described in Laplace notation as, where S is the Laplace transform variable, T is the filter time constant, and K is the filter passband gain.
Electronic low-pass filters. Passive electronic realization.
One simple low-pass filter circuit consists of a resistor in series with a load, and a capacitor in parallel with a load. The capacitor exhibits reactance, and blocks low-frequency signals, forcing them through the load instead. At higher frequencies the reactance drops, and the capacitor effectively functions as a short circuit. The combination of resistance and capacitance gives the time constant of the filter, represented by the Greek letter tau. The break frequency, also called the turnover frequency or cutoff frequency, in Hertz, is determined by the time constant. Or equivalently, in radians per second. One way to understand this circuit is to focus on the time the capacitor takes to charge. It takes time to charge or discharge the capacitor through that resistor. At low frequencies, there is plenty of time for the capacitor to charge up to practically the same voltage as the input voltage. At high frequencies, the capacitor only has time to charge up a small amount before the input switches direction. The output goes up and down only a small fraction of the amount the input goes up and down. At double the frequency, there's only time for it to charge up half the amount. Another way to understand this circuit is with the idea of reactance at a particular frequency. Since DC cannot flow through the capacitor, DC input must flow out the path marked, analogous to removing the capacitor. Since AC flows very well through the capacitor, almost as well as it flows through solid wire, AC input flows out through the capacitor, effectively short-circuiting to ground, analogous to replacing the capacitor with just a wire. The capacitor is not an on-off object, like the block or pass fluidic explanation above. The capacitor variably acts between these two extremes. It is the Bode plot and frequency response that show this variability.
Active electronic realization.
Another type of electrical circuit is an active low-pass filter. In the operational amplifier circuit shown in the figure, the cutoff frequency, in Hertz, is defined as, or equivalently, in radians per second. The gain in the passband is R2 per Rankine 1, and the steuben drops off at 6 decibels per octave, that is 20 decibels per decade, as it is a first-order filter.
Discrete time realization.
Many digital filters are designed to give low-pass characteristics. Both infinite impulse response and finite impulse response low-pass filters as well as filters using Fourier transforms are widely used.
Simple infinite impulse response filter.
The effect of an infinite impulse response low-pass filter can be simulated on a computer by analyzing an RC filter's behavior in the time domain, and then discretizing the model. From the circuit diagram to the right, according to Kirchhoff's laws and the definition of capacitance. Where is the charge stored in the capacitor at time? Substituting equation Q into equation I gives, which can be substituted into equation V so that this equation can be discretized. For simplicity, assume that samples of the input and output are taken at evenly spaced points in time separated by time. Let the samples of be represented by the sequence, and let be represented by the sequence, which correspond to the same points in time. Making these substitutions and rearranging terms gives the recurrence relation. That is, this discrete time implementation of a simple RC low-pass filter is the exponentially weighted moving average. By definition, the smoothing factor. The expression for yields the equivalent time constant in terms of the sampling period and smoothing factor. If, then the time constant is equal to the sampling period. If, then is significantly larger than the sampling interval, and the filter recurrence relation provides a way to determine the output samples in terms of the input samples and the preceding output. The following pseudocode algorithm simulates the effect of a low-pass filter on a series of digital samples. The loop that calculates each of the n outputs can be refactored into the equivalent. That is, the change from one filter output to the next is proportional to the difference between the previous output and the next input. This exponential smoothing property matches the exponential decay seen in the continuous time system. As expected, as the time constant increases, the discrete time smoothing parameter decreases, and the output samples respond more slowly to a change in the input samples. The system has more inertia. This filter is an infinite impulse response, IIR, single-pole low-pass filter.
Finite impulse response.
Finite impulse response filters can be built that approximate to the ideal sync time domain response. In practice, the time domain response must be time truncated and is often of a simplified shape. In the simplest case, a running average can be used giving a square time response.